Welcome back to DeepVisus, where vision meets depth. I'm your host, and today we're embarking on an exploration of one of the most influential ideas in theoretical neuroscience. The title of this episode is Heaviside World, Excitation and Self-Organization in Neural Fields. Our main source for this episode is Neural Fields, Theory and Applications, edited by Stephen Coombes, beim Graben, Roland Potthast, and James Wright. We're focusing on Chapter 3, written by the renowned mathematician and neuroscientist Shun-ichi Amari. Let's start with a guiding question. How can simple mathematical rules lead to the self-organization of complex patterns in the brain's neural fields? Chapter 3 introduces us to the Heaviside World, a reference to the Heaviside step function, a mathematical tool that turns gradual changes into sharp transitions. In this world, neurons are modeled as being either fully active or completely silent, simplifying the mathematics while still capturing essential features of brain activity. This approach allows us to study how populations of neurons interact, excite each other, and form organized patterns, without getting lost in the details of individual spikes. The Heaviside function is a simple switch. It outputs 0 until a threshold is crossed, then jumps to 1. In Amari's neural field model, this means a neuron population is either on or off, depending on whether its input exceeds a certain level. This abstraction makes it possible to analyze large-scale brain activity mathematically. Neurons don't work in isolation. They excite or inhibit their neighbors, and these interactions shape the overall activity landscape. Amari's equations describe how excitation can spread like a wave through a neural field, or how inhibition can contain and shape that activity, leading to the emergence of stable patterns. One of the most fascinating results of this model is the formation of bumps, localized regions of persistent activity, which are thought to underlie working memory and attention. The chapter shows how, depending on the strength and range of excitation and inhibition, neural fields can self-organize into bumps, traveling waves, or even more complex patterns. A key insight from Amari's work is how the threshold for activation determines whether patterns will persist, spread, or vanish. The mathematics of stability analysis, examining when a pattern will remain or change, helps explain how the brain can flexibly store and process information. Although the Heaviside model is a simplification, it captures essential dynamics seen in real neural tissue. For example, it provides a framework for understanding how the brain can hold a memory in place, how attention can focus on a specific region, or how abnormal waves might propagate in neurological disorders. So, let's return to our question. How can simple mathematical rules lead to the self-organization of complex patterns in neural fields? Chapter 3, Heaviside World, Excitation and Self-Organization of Neural Fields by Shun-ichi Amari, reveals that even with the most basic mathematical ingredients, like the Heaviside function, neural fields can spontaneously form bumps, waves, and other patterns. These patterns are not just mathematical curiosities. They are deeply connected to how the brain organizes thoughts, memories, and perceptions. That wraps up this episode of DeepVisus, where vision meets depth. If you're intrigued by how simple switches and thresholds can give rise to the brain's rich tapestry of activity, stay tuned. In our next episode, we'll explore how adding more biological detail changes the story, and what happens when neural fields interact with real-world sensory input. Keep your curiosity alive, and remember, sometimes the deepest mysteries can be uncovered with the simplest tools.